Okay, afternoon. Okay, so last time I think we were talking about induced force, right? Okay, right hand rule. I post a picture using the right hand rule cross product, and that's what these are, okay? Start with index, middle, and the result is your thumb, okay? So in this case, that the right hand rule that I post, if you haven't checked it out, please do that. The pictures according to the product of a vector crossing A cross B. So the order of the cross product matters. Okay, A cross B is not the same as B cross A. So you start with the first vector A, B, and then the thumb. Okay, and here if you look at the equation from the force, this is first vector crossing with second vector. So your index has to be vector L, which is the same as I. Okay. And this is how you get. Now, don't get these are the right hand rule, vector right hand rule. They're not the same thing as machine right hand rule. It's a different matter. Okay. So there's a guy Fleming's right hand rule. It's different from us. Okay. So if please use this one. It's easier to understand, and that's already explained in your textbook already. All right. Okay. So hopefully you practice over the yesterday. Okay. Okay, now let's do an example. Did we do this? Probably not. Okay. This is the end of chapter problems. Okay. So you can check it out. 1-9, I believe. Okay. So all the details of the writings are in that. Okay, but here I'm just going to give you a crude, pictures of what we want to find out. Okay, so we have this red magnetic flux, which gives you directions of B, 0.5 Tesla. You guys can hear me right? I forgot to check.
Yes, sir.
Okay, so here your magnetic field is 0.5 Tesla going toward the right. Okay, you have a conductor, wire. This is W, wire. Okay, or a conductor. Length of 1 meter inside that magnetic field carries a current 2 amp going upward in this case. Oh, I almost forgot. Almost forget. For this class, only this class, 2401, we have to set up a rules that we can agree upon, okay? Don't use whatever you learn in the other classes. We're going to use this rule, okay? So in this box, this is important. For this class, the possible directions for us in a three-dimensional world, right? Okay, so what we are looking at is the plane of the paper. The plane of your paper has to be flat, okay? The plane of the paper. On that plane, this is the right direction, left direction, up. From the plane of the paper, down. And then from that plane, out of page. And the other direction is into page. Okay, that's it. These are the directions for this class. Okay, human directions. So remember, this is based upon the plane of your paper. Okay, now why do I have to tell you this? Because sometimes in the past that I found out, some student would say, hey, this is no, I'm sorry. This is up. This is down. Okay, like down to the page, up, I don't know how. Okay. Wrong. Okay, again, based upon the plane of the paper, right direction, left direction, upward direction, downward direction, into page, out of page. Okay, so the arrow, the tails of the arrow and the head of the arrow tells you which is which. Okay, that's it. Okay, in the past you're gonna have some of you guys can have what, J, K, L, X, Y, Z. No, not here. Okay, because you might have a different textbook, different reference point of view. We don't want to get confused. Okay, so remember that. So if this is the plane of your paper, if this is your paper, so your paper is very thick. See, so this is the plane of your paper. Okay, this is right. This is left. Okay, this is up, upward. You can say upward. Not upward from the paper, it's upward, like a north. Downward. Okay, and then I'm drawing three-dimensional, so this is out of page. Okay, and this is into page. Okay, we have to conform to these rules. Okay, so that way we don't have to argue. We set up this rule for this class. Okay, you must remember that. Again, no XYZ axis, no JKL axis, no PQR, whatever it is. Get rid of that. These are our standards. Okay. All right. Back to our example. Okay, so we have a magnetic field going to right. Okay, and then we have the current going upward in the wire. Length of 1 meter in that magnetic field. So the question is to find the magnitude and direction of induced force on the wire shown above. Okay, again, you use your right hand rule because it's L cross B. L is the same as I, so it's up. Okay, and then you keep that, rotate that, keep that the same, and then your middle has to be on the magnetic field going to right. So it is into page. So your force, you know the direction directly. Direction of the induced force is into page. So we got the directions. Right hand rule of the cross product of the vectors, two vectors. Magnitude is going to be ILB sine theta. And remember, theta is an angle between vector L and vector B. In this case, vector L is upward, vector B is right, so the angle is 90 degrees. You can put this in if you want, 90 degrees. Okay, so we know 2m, L same as I, which is upward. B go to right, theta is 90 degrees. You know all the values given to you, 2m, 1 meter, 0.5 Tesla, sine theta equals 1. So the result is 1 Newton into page. Not shown here. The answer is not shown here. So that's the answer. Okay. We'll come back and do, you got time in the class, we'll do more example on this. Okay. I'm just going to move on to the next topic. So this is the basis of motor action. Because you inject a current, you have a force. So the wire or the conductor is going to move as long as you have the current in that direction. It's going to move into page. And assume that your magnetic field is, also into the page. Okay. Now, why is this the basis of motor action? I'll explain later when we do another example in a more practical manner relating to motor. Okay. Okay, move on to the next one. This time is the opposite of motor. So we have induced voltage on a conductor, again, moving in a magnetic field. Okay, So this time is, of course, as you can guess, this will be the basis of generator. Why is that? Because you move a conductor, moving conductor in a magnetic field, mechanical. The resulting moving of that conductor is induced voltage on the conductor, a voltage. So mechanical to electrical. So this is the basis of generator's action. Related equation is induced voltage, E subscript IND for induced voltage. Okay, E is voltage, is V cross B dot L. Now, don't get confused. It happens, some of the time. V in this case is relative velocity of the conductor to the magnetic field. This is not voltage, it's lowercase v, okay? V, vector V crossing with vector B. Then the resulting product is dot with vector L. And again, L is the same as what we discussed earlier, is the vector length of the conductor inside the magnetic field. And this time, because we don't have a current, unlike the force, right? We know the directions of the current, we know the directions of vector L. Here we don't, because we're doing generators. It's not, if the generator is not connected to a load, it draws no current. It doesn't supply any current. So we don't know directions of L yet. We must assume L. So I underline here, with the length of conductor, its direction must be assumed. Okay. Now the rule for that assumption is that vector L points from negative polarity of induced voltage to positive. Okay, so this is a little bit complex, more steps than the force. Okay, but before we do that, we go back to V cross B, velocity crossing with B. We use the right-hand rule, cross product, to find out the resulting product. Okay, so use the right-hand rule to find the direction of the cross product between V and B. Once you got that, you dot with a vector L. A vector dot vector gives you a scalar. So induced voltage, if I ask you, is it a scalar quantity or vector quantity? The answer is a scalar quantity. It has only a magnitude, no direction. However, it has a polarity, which is not the same as direction. So this is different. Your force is a vector product. You need to know its magnitude, how much force is it, and which direction is it acting upon. See, this is the result of cross product, which is a vector. But this is the result of a first cross product, which you get a vector with dot with a vector is a scalar. So induced voltage is a scalar quantity. Don't get confused. But it has a polarity, not direction, a polarity, negative and positive. Okay. Write this equation, express this one in terms of the final to calculate its magnitude. It becomes V cross B is VB sine of theta 1. What is theta 1? Theta 1 is an angle between vector V and B. Okay. Then you dot with vector L. So in this parentheses, you multiply with L. A dot product gives you a cosine. So it's cosine of theta 2. What is theta 2? Theta 2 is an angle between the cross product of V cross B. It's another vector and vector L. Okay, so you need two angles to determine the induced voltage. Okay, now let's give you a more well numerical example, I guess. So that way you understand better what we're doing. Okay, so I have an example here. 1-8 in your textbook. Okay, not end of chapter. If it's end of chapter, I would write like P1-10. Here, just example in your textbook. Okay, Now, description is in your textbook. You can check on more details of the problem, but here I'll give you the summary of it. Here we have a magnetic field, 0.5 into page. You can see the bottom of the arrows of your magnetic field here. And you have a conductor inside that magnetic field, 1 meter inside. This conductor is moving to the right at 10 meters per second, right? Showing you in the red ink here. Okay, from this setup, we want to find the induced voltage and its polarity on the conductor. So we need to know what happens to the voltage on this conductor and which end is a positive or negative. Okay, two ways of doing it. First step, the easier way is to find the cross product first. Okay, so step 1, find V cross V direction. So we use the right hand rule again. V, right? V, rotate this upward. So V cross V resulting in these two vector is upward direction. Okay, as shown. Second step is to assume vector L. Assume which way. Now the assumption vector L has to be along the conductor length. Okay, so there are two ways of doing it. Okay, you can assume, so I'm showing you a 2.1 and 2.2. 2.1, I assume L points up. Okay, so if you assume pointing up, that means the bottom end of the conductor has to be a negative polarity. The top has to be positive because that's our rule. L points from negative to positive. So if you're going up, bottom negative, top positive. Once you've done that, then you must calculate the resulting values of the induced voltage, which is VB sine of theta 1. And again, theta 1 is an angle between this one and vector L. I'm sorry. Theta 1 is angle between V and B, which is 90 degrees, shown here. So V cross B a sine of 90, which is 1. Okay. And then L a cosine of 0, y0, because V cross B points up, L points up, 0 angle. Also cosine of 0 is 1. Then you substitute V, B, and L in there, you will get 2.5 volt. Positive on the top, negative on the bottom. So this is the answer. Okay. But say, hey, I didn't do it like this. I didn't assume L going up. You say, hey, I like L going down. You can also do that, and it will give you the same answer. Okay. How does that work? So 2.2, assumption of L points down. That means negative is on top, positive on the bottom. And if you know a little bit in both 2.1 and 2.2, your assumptions like that, you look at the induced voltage potential from low to high. The arrow points up, negative to positive, induced voltage. Same thing here, low to high, pointing down. Okay. Repeat the same process. V cross B doesn't change. The angle between V and B is still 90 degrees. However, the angle between the cross product, because your cross products still go up, didn't change, right? The only thing that we did change is L. Instead of going up, like the first assumption, we assume it's down. So the angle between these two becomes 180. The cosine 180 is minus 1. So the resulting magnitude becomes minus 2.5. Excuse me, minus 2.5 volt. Positive on the bottom, negative on the top. Same answer. Let me give you illustrate this. Hang on, let me get a battery. I got a battery that can show you. อนนี้ยังไม่ใช้ก็ถอดแล้ว Okay, this is I have a battery. Everyone knows this is a battery, right? If you don't, you're in big trouble. Okay, 1.5 volt. Assume brand new. Okay, the batteries you can see. Well, I'm assuming everyone knows that the top to the tip. That's a positive polarity, negative polarity. Okay. The normal way when people hold a battery, you hold it like this. I guess I've never seen. Well, I think that's normal because that's the way you can, you know, it stands on the table. And we say this is 1.5 volts. The way we hold it like that. Positive on top, negative on the bottom. Okay. Now, if we do this in, you know, kind of like mathematical notation, it can also do it like this. Not normal. Okay. Most people don't do it like this, but you know, people is not the same. If we do it like that, in our mathematical notation, we say this battery is minus 1.5 volt. Okay. Why? As a it's kind of like a rule of thumb. We say this is lower, this is higher. You know, when you hold it like that, the bottom has to be usually negative, higher is positive. So we say that's 1.5. If you hold it like that, it's minus 1.5. See? So again, it doesn't matter which way, as long as they are consistent, both answers are okay. But to say the induced voltage is minus 1.5 is not common. Okay. All right. But again, 2.1 or 2.2, same answer. Both are right. But this is more conventional. Okay. So please understand what we're doing here. Now let's do extra example. Okay, yeah, I got extra example, including the force here too. Maybe or maybe not. Okay. 1-10. Okay. Now this one is a little bit strange, sort of. Why? Because now your conductor or your wire is aligned at 45 degrees from the y-axis or x-axis. Okay. Magnetic field is the same. Going into the page, 0.5 Tesla, wire of 75 centimeter length in the magnetic field. Give me a second. Oh, I forgot. So back to the example. So you want to write the answer for this one? I'm going to do it separately. You can do it like this. That means from the original picture or setup, this is what you're going to get. Positive, negative. Induced voltage equals to 2.5 volt. You see how that works? Negative here, positive here, right? On top and the bottom. Okay, so this, you know, gives you a better understanding. Illustrations. Okay. Okay. Back to our second example. 1-10. Okay, we have a magnetic field into page. A wire, a line, like I said, 45 degrees from the reference x-axis or y-axis, the same. Okay, 25 centimeter within the magnetic field, and it is moving towards the left. 10 meters per second, shown here. Again, I want to find the induced voltage on this wire and its polarity, which, you know, left or right, has a positive or negative. Okay, we do the same thing. Find V cross B first. Okay, if we do it right, it's going to be downward. I'll show you one more time about V cross B. V. My B is here, so I got to keep V the same. Rotate B into page. B is into page. V is still on the left. My thumb points down. So V cross B is downward. And of course, the angle between V and B is still 90 degrees, as you can see, right? B left, B into page, so it's 90 degrees. So it's exactly downward 90 degrees. Now, assume L. Now, the ways to assume L, okay, if you notice that from the example that we just did earlier, between 2.1 and 2.2, the convention to assume L, the conventional to assume L would be the same trend as V cross B, because that way your angle would be smaller, okay? That would give you a cosine of a positive usually, okay? So we assume it's just, like in this case, L goes up. We should assume L pointing up. I'm sorry, V cross B goes up. We should assume L going up. Same trend. That would result in usually a positive voltage. Here, you do the opposite. You would have a negative, and then, you know, kind of like a strange writing, but it's okay. Okay. So in this case, because L is pointing down, this second example. So how do we assume L? Again, your wire, 45 degrees, right? So this is my wire. I can assume L this way or that way. You know, case A or B. Because we know our V cross B is down. So the easy way is to assume at the same trend. So if this is down, I should do A instead. B would not be wrong, but you know, the angle might be larger than, you know, 90. So both are right. So I'll assume this way first. If we do it like that, this is negative, this is positive. This is your induced voltage. You see how that works? From the assumption. And again, once you connect these two, V cross B going down, L also downward. The angle between the two is 45. This is theta 2. Okay. So your magnitude calculation would be V B sine of 90, the angle between vector V and B, and the angle between the, you know, cross product, and L would be 45. So L is 0.25 meter, cosine of 45. Calculate this, resulting in 0.884 volt. Positive on the bottom, negative on the top. See, shown here. Okay. If you don't like this, okay, you can try like the other way around. I'm not shown in this notes here, but you can also assume L upward. If I do it like that, then my conductor would be like this. Negative, positive, vector L. See, induced voltage would be opposite of A. V cross B is still downward. The angle here is 135, 90 plus 45. Okay, so your induced voltage will become V 10 meters per second. B is 0.5, which is 1/2 Tesla. Sine of 90. L, which is 1/4 of meter, 0.25, and a cosine of 135. This is 1. What is a cosine of 135? Minus 1 over the square root of 2. Calculate this, you should get minus 0.884 volt. Positive on top, negative on the bottom. Shown here. And again, same answer as this. Where's that? Okay. If I want to express this in positive values, I can just multiply it by the negative and then switch this polarity. Okay, I can say, hey, it is equal to 0.884 volt, and then negative on top, positive on the bottom. See, they are the same. Okay, like I said, this is normal, conventional. This is not wrong. You get the same score, but just, irregular. Okay. Now, I give you another problem. 1-11. Okay. Remember, both in force and induced voltage, we have this, equations related. Don't think that some of the time, remember I didn't put the descriptions in there, is that you have to move it in the right direction, or sometimes all the thing has to be in the right direction in order to get a voltage or a force. If you don't do it right, sometimes you get zero value, as can be seen in this next problem. 1-11. Okay. In this problem, your magnetic field is 0.5 again to the right, the blue ink. You have a conductor 50 centimeter inside that magnetic field, moving up 1 meters per second upward. Again, we want to find induced voltage. Okay, start with V cross V again. V, B, into page. See, into page. Now, there's a problem though. I told you earlier that, hey, I should assume L at the same trend as V cross V, but this time it's into page, and the possible of L is either up or down. Which way? This doesn't matter now. Why? Because either L is up or L is down, both will act 90 degrees to V cross B, you see? Meaning what? Meaning a cosine of 90. A cosine of 90 gives you 0, you see? So no matter what assumptions you assume L, this setup will give you no induced voltage, no matter how fast you move the conductor, 0 volt, because you didn't move it correctly. Okay, the orientation of these parameters are not set up to give you a voltage, you see. So the orientation of the magnetic field, the directions of the velocity, the orientation of your conductor matters in terms of giving you induced voltage and induced force. Okay. Let me give you an example on force to illustrate that you can have a zero force, I guess. Hang on a second. Let me check in a chapter. One moment. Okay, 1-9 is a good practice. Now the numbers in a chapter might not match. Hang on a second. I'm trying to. Okay, there's no more in chapter problems. That's going to help us. I'll make up an example for you, I guess. Okay. Suppose let me go back and look at the section notes. Suppose I have a magnetic field going towards the right. One Tesla, right. Okay. And I have a conductor. Okay. Hang on a second, that's the same, right? Let's do it again. Sorry. Cancel that. Into page. Okay. I have a conductor. Let's draw a three-dimensional. Like that. Okay, and then I have conductor, which is a current out of page. You can guess now, I guess, out of page. So we want to draw this in three-dimensional drawings. It's going to be something like this. Kind of like that. Okay, a little bit difficult to see. B is into page. And then you have a wire inside. The current's going out. Okay, as you can see, if this happens, your L cross B would equal to 0. Why? Because your vector L is going to point out of page, right? While UB is into page. So the angle between L and B is 180, right? L cross B is equal to LB sine of 180. This is 0. So you see, So again, the orientation and the movement and the directions of the current matters in terms of finding out the force. See, so this illustrates another example that not all cases would give you non-zero induced force. You have to move in a proper directions. Okay. Okay. Again, now let's see how do we use this concept for generators or motor. Okay. And hang on, I almost forget. I sent you the example before class. Let's do that. Okay. Let's make that a practice example that's related to the magnetomotive force and the ferromagnetic core. We'll do the additional example today. Okay. To help you guys practice before we're finishing chapter 1 today. This is all the materials in chapter 1. Okay. So you have that. Let me, I gotta write my own example. Hang on. Let me open mine. The current for A, 200 turns, right, is 2.5 amp. B is 400 1 amp. C is 100 turns, 4.5 amp. Okay, and cross-sectional area, 5 centimeters square. Length is 75 centimeters. Okay, and 3 to 9. Okay. Just let me know if I'm not using the right number. Okay. So you should have this post, but I'm just going to give you a rough drawing. So we have a core. Okay. 3 coils, A, B, and C. Now, the directions of the current in these coil matters. Okay. Coil A has 200 turns. B 400 turns. C 100 turns. Okay. A has a current of 2.5 amp shown here with the arrows. Okay. B 1 amp with another arrows. Only one shown, but you should know it's the same directions. C again shown with the arrows. Okay. What do you want to find? I forgot. What is the problem asking for? Net flux direction and magnetic flux in the core. Okay. I'm going to find the net magnetic flux, and its direction. Okay, so what does this mean? Means that each one would produce its own magnetic flux, but all three are doing it at the same time, so the net would be the sum of the three. Okay, so start with finding out the directions of each one. Right hand rule again. So phi A going up. So this is my phi A. Okay, and it's gonna loop this. See, so I'm saying phi A, CW direction. Okay, phi B again. So phi B would be the same direction. So phi B also CW direction. Okay, phi C going down, so towards the right. So the last one from coil C is going to be counterclockwise. Okay. Now you can use the notation on your own, but you got to be consistent. So let's assume I say, I'm going to do like what we started with a class. It's counterclockwise positive, clockwise negative. It's negative. Okay. So your phi net is the sum of the three. Phi A plus phi B plus phi C. But phi A and B has a negative value. See, phi C has a positive value, so they have to be canceling each other out. Not out, canceling each other, deducted from, phi C. So and the resulting measure phi net would give you the directions of the net flux. Okay. Now, if we do this, we started out with the magnetomotive force, because each coil will give you amperes turn, right? So we say that coil A is going to give you magnetomotive force A, which is NA times IA. Similarly, B would be NB, number of turns of coil B. This is number of turns of coil A, IB. And again, C is going to be N sub C, I sub C. Okay, and these has a sign according to the directions of it. And the sum of the three would be your net magnetomotive force. A plus B plus C. But this is associated with the flux direction. So that means if I put that in, it has to be negative magnetomotive force A, because it's clockwise. We assume clockwise negative. You can do the opposite if you want. Negative of that B, positive of that C. Then you put these in there, the turns of A, turns of coil B, turns of coil C, the current in each windings. Let's do that together here. So it's going to be 200 turns times 2.5 amp. Negative, don't forget. Another negative. B is 400 turns, 1 amp, plus C, 100 turns, 4.5 amp. Okay, so calculate each. This is going to be 500 amperes turn minus 400 amperes turn plus 450 amperes turn. So the resulting net magnetomotive force equals to minus 450 amperes turn. This would give you phi net direction negative, so is in CW direction. So first answer is the directions. Okay. Now, what about phi, the magnetic flux? Okay. We have to use a table given to you that depends on the core materials. Okay. B and H table, so you don't need to know mu, or you can calculate mu using the ratio B and H. Okay. But to do that, first you have this number, the magnetomotive force. Okay. What is that got to do with phi? So how do we do this? You have to use Ampere's law, if you remember. Okay. What is Ampere's law stated? If you've forgotten, go back to the lecture notes. I guess I can do this here. Let me grab the notes for you. Forgot what page it is. And I equals to HLC, I guess. Okay. So from Ampere's law, what you're going to get is an I net is equal to HLC. See? Remember that? This is net magnetomotive force. Must equals to H times LC. Okay, now we know the net earlier. We can omit the negative sign because the negative sign only helps with the directions. Okay, you know which way it's going to flow in the core, so we can get rid of that. Now we know LC given to you as 75 centimeters, which is the magnetic path. What about H? Okay, we need to know H. How does that work? You must calculate H. Remember, our goal is to find phi net. Where's that? Okay. What does phi net has to do with H? We know another equation for us is B is equal to phi over the area, right? So we want phi. We need to know B. We know the area. So here it leads to phi is equal to BA. We don't have B yet, okay? But we can find B from mu H. But in this problem, we don't know mu. However, we have this table. If I know H, I can find B. I know B, I can find phi. See? So here, we know the net magnetomotive force 450. Use that to find H from this equation, starting from Ampere's law. And you find H. Once you get H, locate it on the table and find B. Once you got B, multiply it by the area, you get phi. Okay, let's do it here. So here, H is the net magnetomotive force is 450 amperes turn divided by the length, which is 0.75 meter. What is that number? Is that 400? Give me a second. I don't have a calculator. 4, 3, 15. Yeah, 600, right? 600 amperes turn per meter. You got H for your material now. We'll locate it in the table here. So from the table, this will give you a B of 0.75 Tesla. Okay. So therefore, your phi equals to 0.75 Tesla times the area, which is 5 centimeters square. 5 times 10 to the 4th meter square. So the answer becomes 0.375 Weber. Is that right? Hang on a second. 0.375 milliweber, or 3.75 times 10 to the negative 4th Weber. See? So this is how you calculate the net magnetic flux in the core. You have to take into account of all the windings in the coil. And its directions of the current matters, which way is it flowing. In this case, A gives you a clockwise flow in the core. B, also a clockwise flow in the core. Going to be running out of battery again. Okay. C opposes those two, counterclockwise direction. So it has to be subtracted from these two. But in this case, we assume clockwise to be negative, counterclockwise positive. Okay. That's why we get a negative. You can do the other way around. You can say positive, positive, this must be negative. You can get 450. But you just use that sign to determine the directions only. Once you want to calculate H, you omit that sign. So it becomes 450 in this case, divided by LC, which is 75 centimeter or 0.75. You get 600 amperes turn. You can use either mu H, if you know mu, or in this case, you have a table already. You can find B right away, knowing H. Okay. Once you get B, then you multiply it by the area to get flux. Okay. So this is how you make use of the ferromagnetic materials, you know, magnetic flux and intensity relationship. Okay. Let's do an example on magnetic circuit. We have about 20 minutes, right? Okay. What I'm showing you here. Let me send you the second one. This is the last semester classwork assignment. Okay, let me post it to you. Give me a moment. Okay.
The question.
Yeah.
Question: does you explain we have to use right hand rule or not? Use to, right?
Yes. Yes, you have to. Hang on. Let me send. You have to. You don't use the right hand rule, you won't know the directions.
Could you explain the use right hand rule in this question again?
Look at the directions of the current. Hang on a second. Let me go back to the camera. Hang on. Slow. Okay. You number one, if you look at the problems that I send you, look at the windings for A. Okay. Let me screen sharing. I'll try. Okay. No, I can't. I got to use my right hand to show you too. I guess I can redraw. Hang on a second. Okay. Okay, this is your core, right? If you have the problem, look at it, and then you can come back here. Okay. Coil A, the drawing matters. Look at the drawings of the curly wire. Okay. Which one overlaps which? Forgot. Okay. Okay. Now, A has an arrow on the top of the core. One arrow, I think. Right? This is A. B has an arrow on the top of the core, like that. C, where's the arrow C? Pointing down. Okay. Because the directions in A is that way, right? That means it's going to loop on the back, coming out. So this the other one, not shown in the problem, but you must know, has to be in the red direction, same, right? That you use your curly right hand rule to find the directions of the flux inside the core. Remember, the flux flowing in the core either this way or that way. I mean clockwise, if you look at the plane of the paper, or counterclockwise. Which way? We have to know. For coil A, right hand rule. See? Wrap around, going up. So VA would go starting up and continue with the core structure. Okay, so saying VA is in CW direction. You must use the right hand rule, and you must know the flow of the current directions in the coil. Okay, similarly in coil B, look at that current. I gave it to you in the beginning. You do the same thing. If one's going that way, the rest has to be the same. You can't, it's not possible for one to go that way, the other goes the other way. Obviously, by logic, if that one goes to the left, this one has to be the same. And again, right hand rule, curly or the current. I can't bend. Can you do that on your own? Try that. That's going to go down on that coil. So B would go like this. And it's going to continue to flow in clockwise direction. So phi B is also in clockwise direction. See, so if I assign, if I give it a positive or negative, let's say I say it's a positive, I can say it's a negative if I don't want to do it. But earlier we did a positive. Let's say I say it's negative and negative. Okay. C. Again, if that one goes down, the other one must be down. Right hand rule again. Now this time, it's going to go to the right of that coil. But if continue, it would flow in counterclockwise direction. So C would be different from the other two. CCW, if it's different, the sign of phi C has to be positive. You can do it like this, or you can do positive, positive, and negative, whichever one it's you like. Okay. Then, once you know that, each one, remember this has a magnetomotive force of A, B, and C. Number of turns times the current, like shown here. They all have to add it together to get the net one because both are doing at the same time. Sign, B is opposite, so it has to be positive. If you assume, negative, negative for clockwise, positive for counterclockwise. But if you do it the other way around, if I do, this is case 1, if I do case 2, you like that, your net would be A plus B minus C, because C is different. Then the resulting is going to be positive 450 amp. Positive means clockwise direction still. Same answer. Okay. Give me a second. I'm going to be running out of battery. Hang on. Let me get a charger. So does that answer your question?
Yes, Ajahn.
Okay, make sure you understand, all of you, make sure you understand what we're doing here. Okay. Example like this used to be in the midterm exam also sometimes. Okay, you gotta understand the concept though. Okay, how that works. Okay. I guess we have time, about 10 minutes. I send you the second example relating to the magnetic field. We can do this together, I guess. Okay, you have a magnetic structure. Okay. Okay, so this is similar to the example they give you in class, a 3-legged core. Okay, dimensions are given. So you can basically sketch the magnetic circuit in a simple manner because we know the winding is in the center leg. So I start do that again. N times I, and the center leg. Let me kind of like do it like this. I'm gonna draw the core pretty fast. You get 2 air gaps, right? So actually, I just changed the number so you can find practices on your own if you want. Okay, 2 air gaps. The numbers is different from the example they give you in class. So I suggest you should practice this. You have these windings here, either left or right, and then gap 1, gap 2, right? You have the dimensions, okay? Again, you look at the path of the flux. It's the same, okay? So here, center leg, PC, splits to the left and right, Phi right, Phi left, see, again, completes the path, same thing, okay? So again, to, get a magnetic field based upon this, you look at the source, which is the magnetomotive force, and then the flux, okay? So I get that magnetomotive force, PC passing through from this point. Now don't get confused. I guess if we have time, next week we'll do one more. This is symmetrical, so it's kind of like a simple. So this is the length of center core. Okay, so that's RC. BC. Again, then splits to the right, this whole length. Splits to the left, this whole length, and passing through the core and the gap. That's why. Let's go like that. R right, RG2. Okay, go to the left. Similarly, R left, RG1. See? Phi left, phi right. Okay. Then the rest is the same, just like the example in your notes. Okay. So the important part is to find out these related length to the reluctances. Okay. RC, I will re-emphasize it here. Okay. RC, okay, so we start with RC is L inner center leg divided by mu A. Okay, A is the same, 25 centimeters square, I think. Okay, so that's given. Now LC, again, it's from this path, the red ink, down to here. Okay, so that means LC must equals to, what is that, 5.5 plus 15, I think, right? Plus 5.5. And this is centimeter. So we're going to convert to meters, so 10⁻² meter. So far so good, right? That's LC. This is 5. So half of it is 5.5. This is 5. And these are 15, I think. Okay. Now, L right. Then you just substitute these in there. Okay. Now my R right has to be L right divided by mu A. Okay, mu and A known. Now L right. L right. Now, this is the one that, you know, people get confused. Let me see, you can, well, I'll do the red ink. L right starts from this point where the splits of the flux starts. Okay, and then it's going to go from here, come down, completes until this end. See? So to resketch in the core, starts from here, down here. See, this is L right. You see what we're doing here? From this point where the splits of phi left and right starts, completes down till it merges again. That's the totaling of L right. Okay. So in this example, in this assignments, LR is again 5.5. The top end is 5.5 plus 5.5 plus 15, right? On the top end, in the center, it's the same. On the bottom is the same, so I just multiplied it by 3 and convert to meter. See, you'd have to add all together, just if it's symmetrical, now top, right, and bottom. Okay, and again, because your core in this problem is symmetrical, so R left would also be the same, which is L left. Same thing. Okay, actually they are not the same. Why? Because G1 and G2 has to be subtracted. But again, G1 and G2 can be neglected because they are very small compared to its length. Okay, so this is actually an approximated value, but a good approximation. Okay, then you just calculate. Okay. Okay, now, I suggest you go home and do this as a practice problem. Okay. And we want to find, and this time, don't forget, in this problem, there's no fringing effects, I think. Okay. So I'll give you the answer and come back and show. I'll post a solution next week so that way you can practice. Okay. So these are the answer. Phi C in the center leg is 3.726. You might want to write this down. Milliweber times 10 to the negative third Weber. Okay. Phi right 1.315. Again, milliweber or 10 to the negative third. Phi left 2.411. Notice that left and right added to get that, because that's what we have on the magnetic circuit. Okay. And then BG1 0.9644 Tesla. BG2 0.526 zero, I guess, Tesla. So these are the answers for this problem. Go home and, on the weekends, try to do this for your own sake, because these will be in the midterm exam, a variation of it anyway. Okay. All right. Yeah, I'm out of time, right? Yeah. Okay. So, and then we'll come back next week. I'll give you detailed solutions, either post it or, I don't know, explain it. We'll see. So again, so I suggest this is, you don't have to submit. I'm not giving you a classwork assignment yet, but you should try to do this. Follow the example in the lecture notes that we did, because the core are pretty similar. I just changed all the numbers. That's it. The rest is the same, and try to do that with one exception: no fringing effect in this problem. No fringing effect, meaning what? AG exactly go to AC, so you don't have to multiply with 1.05 or anything like that. So it's even easier. Same cross-sectional area. Okay, and see if you get these answers or not. Okay, I'll stop here for today. Any questions? We are finishing chapter 1 today, I think. Yeah. No questions? All right.
No, sir.
I'll see you next week.
Thank you for today, Ajahn.
Thank you,
Okay.
sir.
Stay healthy and stay safe. Okay, bye.
Thank you, sir. See you next week.
Thank you, sir. Thank you, Ajahn.